What specific problem does the star attention algorithm aim to solve within the context of long context inference for large language models?
The star attention algorithm addresses the significant computational and memory challenges associated with long context inference in large language models, LLMs, particularly due to the quadratic complexity of the self-attention mechanism. It specifically targets the inefficiencies in processing long sequences by employing a two-phase approach. First, it divides the context into contiguous blocks for local attention, which reduces complexity from quadratic to linear, and second, it utilizes global attention for query processing and token generation. This method allows for efficient context processing across multiple hosts without interblock communication, thus enhancing scalability and inference speed. Additionally, star attention incorporates an anchor block mechanism to manage attention spikes and ensure that the attention distribution closely approximates that of global attention, thereby maintaining high accuracy while significantly speeding up inference. Overall, star attention enables LLMs to handle longer contexts effectively while preserving performance.
How does the proposed star attention algorithm work? Please illustrate it step by step, detailing both phases of the algorithm.
The star attention algorithm operates in two distinct phases: context encoding and query encoding with token generation. In the first phase, context encoding, the input context is divided into contiguous blocks, with each block prefixed by an anchor block, the first block. This creates augmented blocks that allow each host to compute self-attention locally over these blocks without inter-host communication, reducing the attention complexity from quadratic to linear. The key value KV vectors for the current block are retained in the cache, while those for the anchor block are discarded to prevent attention spikes that could disrupt the attention distribution. In the second phase, query encoding and token generation, the query is broadcasted to all hosts, which compute local attention outputs using their respective KV pairs. A designated query host aggregates these local outputs and computes a global softmax denominator, ensuring that the global attention scores are normalized correctly. The query host then generates the next token and updates its KV cache, repeating this process for each subsequent token. This two-phase approach significantly enhances inference speed while maintaining high accuracy, closely approximating the performance of full global attention.
Can you provide a detailed example that walks through the main algorithm steps of star attention, specifically using a simple input sequence?
To illustrate the main algorithm steps of star attention, consider a simple input sequence consisting of a context, C, with 3 blocks and a query, Q. Let's say the context is divided into 3 blocks, C equals C_1, C_2, C_3, where each block contains B tokens. In the first phase, context encoding, each block is prefixed with the first block, C_1, to form augmented blocks, C equals C_1, C_1, C_2, C_1, C_3. Each host processes its assigned block, C_I, using local blockwise attention, generating key value KV vectors for C_2 and C_3, while discarding the KVs for the anchor block, C_1. In the second phase, query encoding and token generation, the query, Q, is broadcast to all hosts, where each host computes local attention outputs using its KV pairs. The designated query host aggregates these local outputs and computes the global attention by summing the local softmax denominators. Finally, the query host generates the next token based on the global attention and updates its KV cache with the new token's vectors. This two-phase approach allows star attention to efficiently handle long context inference while maintaining high accuracy, as detailed in the paper.
What are the theoretical or practical benefits of using star attention over existing methods like ring attention?
Star attention offers significant theoretical and practical benefits over existing methods like ring attention, primarily through its two-phase approach that enhances computational efficiency. In the context encoding phase, star attention reduces attention complexity from quadratic to linear by processing context in contiguous blocks without inter-host communication, unlike ring attention, which requires a ring communication pattern. This leads to up to 11 times faster inference while maintaining 95 to 100% accuracy compared to baseline methods. Additionally, star attention's use of anchor blocks effectively mitigates attention spikes, allowing for a more accurate approximation of global attention without the need for extensive interblock communication. Furthermore, star attention is compatible with other optimization techniques, such as flash attention and KV cache compression, enabling further speed enhancements during inference.
How is the performance of star attention validated in the experiments? Describe the experimental design, datasets used, and the metrics or benchmarks applied to demonstrate its effectiveness.
The performance of star attention is validated through a series of experiments using the LLM-A3.1 models on the ruler and Bobby-Long benchmarks, which encompass various tasks requiring long context processing. The experimental design involves comparing star attention against the baseline ring attention, focusing on metrics such as inference speed and accuracy across different sequence lengths, specifically from 16K to 128K tokens. The ruler benchmark consists of 13 tasks categorized into 4 domains: needle in a haystack, retrieval, multi-hop tracing, aggregation, and question answering, while the Bobby-Long benchmark assesses tasks that require multiple supporting facts. Results indicate that star attention achieves up to 11 times faster inference while maintaining 95 to 100% of baseline accuracy, with accuracy degradation limited to 0 to 3% across tasks. Additionally, the experiments explore the impact of varying block sizes on accuracy, illustrating the trade-off between speed and precision, further validating the effectiveness of star attention in long context scenarios.
What specific results were achieved by applying star attention on the LLM-A 3.1 models, including the improvements in inference speed and accuracy compared to baseline methods?
Applying star attention on the LLM-A 3.1 models resulted in significant improvements in inference speed and accuracy. Specifically, star attention achieved up to 11 times faster inference while maintaining 95 to 100% of the baseline accuracy across various long context benchmarks. In comparison to the baseline method, ring attention, star attention demonstrated similar accuracy to full global attention, with relative accuracy degradation limited to 0 to 3%, while providing up to 5x speedup at sequence lengths of 16K to 128K tokens. Furthermore, larger models like LLM-A3, 1 to 70B instruct experienced even greater speedups at any given sequence length, reinforcing the effectiveness of star attention in optimizing long context tasks. Overall, these results highlight star attention's capability to enhance computational efficiency without significantly compromising performance.